Related rates, rocket and camera. A camera that will track a rocket launch is positioned on the ground 1,000 meters from the launch pad. The rocket is launched and travels directly upward. The camera always points directly at the rocket. When the rocket is 1,000 meters high, its speed is 200 meters per second. A. At that time, how rapidly is the distance between the camera and the rocket changing? B. At that time, how rapidly is the angle of elevation of the camera changing? This is a fairly typical related rates problem, and we will do both parts. And we'll start with A. The process that we follow when we solve a related rates problem is generally the following. First, if possible, you want to draw a picture that describes the problem. Next, you want to assign variable and constant labels to that diagram based on the problem information. From that, you want to find a relation between those variables that holds throughout the problem, not just instantaneously, but throughout the problem. 4, you want to implicitly differentiate that relation to obtain the related rates equation. And then finally, 5, substitute instantaneous information and solve for the desired rate. Okay, so first, we draw a picture. And in this particular case, we have the camera pointed at the rocket, which is flying straight up, and you can see that there's a right triangle. Next, we need to assign variable and constant labels based on the problem information. And one of the things that's obvious is that the camera is always 1,000 meters from the launching pad, so the base of the triangle is 1,000. Now we're given information about the height of the rocket and the speed of the rocket, which is going to be the derivative of the height. So we clearly are going to have to include h, the height of the rocket, as one of the variables. Finally, we need to find out how rapidly the distance between the rocket and the camera is changing. So the last variable has to be d, the distance between the rocket and the camera. Now we are looking for a relationship between the variables, and that's pretty obviously given to us by the Pythagorean theorem, which says that d squared is h squared plus 1,000 squared. The next step is to implicitly differentiate the relationship. So the derivative of d squared is 2d times the derivative of d with respect to t. The derivative of h squared is 2h times the derivative of h with respect to t. And the derivative of 1,000 squared is 0, since 1,000 is a constant. Finally, we're going to substitute in to the related rates equation and solve for the rate. Now, according to the problem, when the rocket is 1,000 meters high, its speed is 200 meters per second, which means that h at the instant we care about is 1,000 meters, and dh dt is 200 meters per second. Now, we need a value for d, and that's going to come from the Pythagorean theorem. 1,000 squared plus 1,000 squared is d squared, so d ends up being 1,000 root 2. We plug that into the related rates equation, and we get 2 times 1,000 root 2. Derivative of d with respect to t is 2 times 1,000 times 200. Solve for the derivative of d with respect to t, and you end up with 100 times the square root of 2 meters per second being the rate that the distance between the camera and the rocket is changing at the instant in question. Now let's do part B. And the difference in part B is what we care about now is how rapidly the angle of elevation of the camera changes. So we draw the same picture that we drew in part A, but the labels are going to be different. The base is still 1,000 meters. The height is still h, but now we don't care about the distance between the rocket and the camera. We care about the angle that the camera makes with the horizontal, and we use the variable theta to denote that angle. Now we want to find a relation between the variables, and the obvious relation is that h divided by 1,000 is the tangent of the angle theta. So we differentiate this expression implicitly. Derivative of tangent is secant squared, so we get secant squared theta d theta dt equals 1 over 1,000 dh dt. Here we're thinking of h over 1,000 as 1 over 1,000 times h. Now what we do is find the instantaneous information and substitute back in. The rocket, per usual, is 1,000 meters up and is going 200 meters per second. But we need a value of theta, and what we can see is that the angle at this particular instant must be pi over 4 because the tangent is 1. And now to calculate the secant of pi over 4, we notice that the secant of pi over 4 is 1 over the cosine of pi over 4. Cosine of pi over 4 is 1 over root 2, so the secant is root 2. Now plugging into the related rates equation, we get the square root of 2 squared. D theta dt is 1 over 1,000 times 200. And solving for the d theta dt, we finally obtain that d theta dt is 1/10 radian per second.